Welcome students. Today we will discuss systems in the next part of signal and systems. A system may be defined as any entity that acts on an input signal and transform it into an output signal. A system may be defined as a set of elements which are connected together and produce an output in response to an input signal. This is the second definition. The response or output of system depends upon the transfer function of the system. This transfer function is represented by this T value, that is transformation. It transforms the input into output. For example, a mathematical system where this system always square the input and add the 5 in the input. That is square plus 5. X is the input, y is the output. Y becomes x square plus 5. Suppose x is equal to 2, then y becomes 2 square plus 5 equal to 9. So this is a system having a constant input relating to a constant output, specified output respect to that input. There are various types of systems such as electrical system, mechanical system, biological system, optoelectronic system, electromechanical system, communication system, etc. Physical devices such as motor, amplifier, filters, boiler, turbine are examples of systems. Motor, amplifier, filter, boiler, turbine are examples. Television set is also interconnection of small systems like tuner, IF amplifier, video amplifier, sound amplifier, etc. So we can see that we are surrounded by infinite systems. There are a lot of systems. Okay, so this is the representation of system. Now on the basis of time domain, study of time domain or operation in time domain, we can divide broadly system in two parts, that is continuous time system and discrete time system. For example, amplifiers, filters, integrator, differentiators may be put in continuous time domain system. Similarly, discrete time microprocessor, semiconductor memories, registers, and so on, discrete values, this can be studied in discrete time systems. Also filters, there are digital filters also which are in this particular discrete time systems. There is analog filters we are talking about. So symbolically, only difference is here T shows the continuous time, here N shows the discrete time. That is Yn T xn and Yt T xt. For example, an RC circuit fed by an input voltage, and if output is considered to be at the capacitor end, then this will be characteristics equation of this circuit. We will see it later, we will derive it later, and it is a differential equation basically. So this is a type of system, continuous system. Similarly, for a simple system having a input, adding the input and delayed value of input will be added and forming output, it is a simple discrete system. Okay. Further, it is also known as difference equation because it deals with the difference. There are xn minus 1, xn values are different values, and it is differential equation. D by dt is here. First order differential equation with 1 upon RC is some constant depending upon value of R and C. And VST is the input, VCT is the output. Further, we can classify the systems such as first is static system, memoryless, and dynamic system with memory system. If output at any instant of time t depends only on the input applied at that time t, but not on the past and future values of input, then it is known as static system. For example, x square t, x square in discrete domain, x square n, this output at a time equal to t is dependent upon at input at the time equal to t. Both the values are time equal to t or time equal to n, discrete time. Or in practical case, current flowing through a resistor, a physical resistor, is an example of static system. Okay. Then current flowing through a resistor or voltage flowing through a resistor, voltage measured across resistor, both are example of static system. In dynamic system, output depends upon present or past or future values of input. It may be any combination of these, but it must contain past or future values because it must have some storage element. For example, differential equations, RC circuit, because C capacitor is a storage device, charge storage device, so it must have some differential equation as we have seen in last slide. That is, the capacitor contains, this is due to this capacitor we have that differential equation. For discrete time domain system, suppose difference equation, all the systems shown by difference equation, we have already studied difference equation. This is the difference equation, example of difference equation, xn plus xn minus 1. So for example, practical example is accumulator, which adds all the previous values or the past values of input. That is, yn is equal to k is equal to minus infinite to infinite xk. That all the values are added, forming the output. Second type of system is causal and non-causal system. Causal systems are output depends only on present and past value. Now here past value is there. So for it means response of system does not begin before the input function is applied. Response of system does not begin. For example, we are going to experiment something and output should not come before the input is applied. Then this is the causal system. So all real-time systems are causal because real-time means if we give the value in real time, the output will comes out after that only. So all real-time systems are causal system. For example, y is equal to xt minus 2 plus 2xt. When t equal to 0, we have some past values. Okay, we have some past value, that is t minus 2. Okay, similarly, it is yn is equal to nxn. Now, non-causal systems when output depends upon future value also. Okay, future value means yt equal to xt plus 2 plus xt. Suppose now we have this value. Suppose at t equal to 0, we must know the value of at t equal to 0, we must know the value of x2, that is future value, next after two time instant values. That is what this every t plus value is the future value. So it is what a non-causal system. Similarly, for this special case, for n equal to 1, suppose n equal to 1, we must know the x2, that is twice extra value. For x and n equal to 2, suppose for y2 is equal to x2 plus x4. So for n equal to 2, we must know value of x4. It is what? Future value. So if we know the future values, then these systems are non-causal systems, which are generally not used practically. But we should avoid the conditions of non-causal system. For example, y equal to x minus t. Suppose at t equal to minus 2, then equation becomes x2. That is, at t equal to minus 2, we must know the equation value of x2, which was the future value. Similarly for xn. So these are causal and non-causal systems. Next is linear system. Linear systems are which obeys the principle of superposition and principle of homogeneity. Otherwise, all the systems which does not follow these properties are known non-linear systems. Okay, what is homogeneous property and superposition property? If yt is the transformation due to input xt, then if a constant is applied at input, then it must reflect at the outputs similarly. That is what homogeneity. If a xt input applied to the system, then it must result a by t, where a is some constant. Similarly, superposition theorem says that if there are input x1t applied to the system causing the output y1t, and in the same system, if second input x2t is applied and will result output y2t, system is same. System is same, that is t is same here. The two inputs are different, corresponding to two different outputs. Then, if we apply addition of both the inputs to the system, the response of system will remain same and it will result simply addition of both the outputs, both the individual outputs. Okay, this is superposition theorem. So linear system are those which follow property of both. So combining both the principles, that is a1 y1t plus a2 y2t must be equal to a1 x1t plus a2 xt. Put it in the system T, transformation T. Okay, when two inputs with two scalars with two constants are applied, then it results the summation of two outputs, which are the individual outputs of the inputs and with the same constants. Okay, we will discuss it in detail because it is very important type of system with the help of some examples in the next lecture. For example, linear systems are filter, communication channel. These are the practical examples of linear systems. Okay. All other system which does not obey this property are non-linear system. Next is time invariant system. It is also very important type of system. If its input output relationship does not vary with time, then it is known as time invariant system. Invariant, not varying with time. If input and output relationship does not vary with time, or it means time shift in input signal results in corresponding time shift in output. It means if input is delayed and fed to the system, corresponds some output, it must be the simply delayed output by which input was delayed. So output due to delayed input must be equal to delayed output, or time shift in input must reflect in time shift in output. Okay, then it means that it is not varying with time. And these systems are very important. If yt corresponds to input xt, then xt minus t input will result yt minus t. The time shift is the same. Time shift is the key here. In discrete time domain, these systems are called as shift invariant because here we use the term t, continuous time. In discrete time domain, we use the term n. So n minus 1, n minus 2, n minus 3 and so on. These are shift. That is what shift invariant. These two are very important types. So we will study more in terms of examples later on. Next is stable and unstable system. Bounded signal has always finite value of magnitude, that is gt. Suppose any signal gt having the magnitude less than or equal to m, where m is some positive real finite number, that is it is bounded by this m. Okay, for example, sine wave. Sine wave is what? Bounded by upper and lower level. It will not go beyond that upper and lower level. These are bounded values. This is the sine wave, that is well. So a stability means a bounded input, bounded output stable system produce a bounded output or bounded input. Means when a bounded input is applied to a system, then it results a bounded output, the output which is also bounded by some integer. For example, if xt is the input applied and it is bounded by some means mx, which must be obviously less than infinite for all value of t, then putting the input in the transfer function and getting the output yt, and that yt should also be bounded by some value my. Okay, and it should also be less than infinite. Mx, my are positive real numbers. So bounded input results bounded output. Then system is known as bounded stable, otherwise system is unstable. Necessary and sufficient condition for a system to be bounded input, bounded output stable is because a system can be represented in terms of its impulse response. A system, suppose here is a system, input and output are there. When impulse is given, the response corresponding to the impulse by the system is known as impulse response of the system, that is represented by ht. So for any system to be BOC stable, bounded input, bounded output stable, that is necessary and sufficient condition, very important, that is impulse response should be finite for overall duration, minus infinite to infinite, integrating for complete duration, its impulse response should be finite, that is less than infinite, always should be finite, and it is the necessary and sufficient condition for a system to be stable in bounded input, bounded output criteria. So these are basic types of systems, classification of system. Definitely there are other classifications also, but we will not study because of this subject does not deal there value so much. Such as invertible and non-invertible systems are there, which can be inverted, which can be revert back. It is invertible system. If the system has unique relationship between its input and output, the system is invertible. Otherwise, it is non-invertible. Further, we can divide the system as a finite impulse response, infinite impulse response system. It means when impulse response of system can be defined in finite number of samples, then it is finite response. If it's not defined by finite number of samples and infinite number of samples are used, then it is infinite impulse response. Next, maybe lumped parameter system or distributed parameter system. The lumped parameter system is in which components is lumped at one point in space. These systems are described by ordinary differential equation, whereas distributed parameter system may be in which signals are function of space as well as time. These systems are described by partial differential equation, but these systems are not used here. These are the most important classification, 5 classification, which is very important in signal system course. So thank you very much for watching, and in the next video we will study this examples of these type of system, which is more important, because without example we cannot able to classify the system, identify the system. Okay, thank you for watching.